Okay, I guess we're ready to start now. My name is Bill Bilodeau. I'm with AMD, a developer technology engineer. Sorry I'm not wearing green today, but I'm on the red team. So, our talk today is going to be on Vertex shader tricks and ways that you can use the Vertex shader to get better performance. Some of the topics I'm going to cover today include a little brief introduction of the DX11 front-end pipeline. I'm going to talk about some of the common bottlenecks with that part of the pipeline. And also going to talk more concretely about some specific features, and then how you can use those features in an actual game. And I'm going to also give some performance results, too. So you've all seen this, I'm sure, many times. This is at least the first part of the DX11 pipeline, the front-end part of it. Starts with the input assembler, which is feeding vertices to the Vertex shader, of course. And the hull shader follows that with control points, which get passed to the fixed function tessellator, which then gets past the domain shader, and then at the bottom of this part of the pipeline is the geometry shader, which is dealing with primitives. One of the newer features which started with DirectX 11.1 is the ability to write or to bind a UAV as output to any one of these shader stages. So you're used to seeing the pipeline like this, but you know, of course, that in hardware, it's much different. There's a lot of parallelism going on there, hundreds of thousands of threads being executed at the same time. You have multiple stages executing at the same time, vertex shaders, pixel shaders, all being executed at the same time. So it's not that nice, clean, linear pipeline. Although to the programmer, it looks that way. So some of the bottlenecks for the vertex shader to consider, one of them we've seen are with vertex attributes. And particularly on AMD hardware, you want to limit your vertex attributes to 4. This is because the way there's a limitation on vertex attributes that are passing between shader stages. So this applies to all of the shader stages, except of course the pixel shader, which is at the end of the pipeline. Also, texture fetches are something to consider. They can add latency to the vertex shader. In particular, dependent texture fetches, where you're fetching a texture coordinate. One thing to do is to offset those texture fetches with ALU operations to hide the latency. And a good way to do this is to group those texture fetches all at once. So you don't want to do the type of thing where you're doing a texture fetch and then process that data, texture fetch, process the data. You want to just do all the texture fetches first so that you can have that latency hidden. Another thing to consider with the vertex shader are the caches. And you've got a pre-vertex shader cache and a post-vertex shader cache. The pre-vertex shader cache is mainly for hiding latency. And the post-vertex shader cache allows you to reuse vertices. Now, you want to use these caches wisely. In particular, you should avoid very large texture formats because they take up more space in the cache, and so you don't want to use up all of that cache space. And for making the best use of the post-vertex shader cache, you want to use draw indexed, because anytime the hardware sees the same index coming through, it'll reuse the already processed vertex and just bypass the vertex shader. For the geometry shader, it has some nice features. It can add and remove primitives. However, adding new primitives can require storing new vertices. With a lot of data amplification, it could mean going off chip, and this is going from a fast on-chip memory to much slower off-chip memory, so it becomes a bandwidth issue. Also, what you don't always consider is that when you start using the GS, it's another shader in the stage, another shader stage in the pipeline. And as I mentioned earlier, all of these shader stages are sharing the same resource, right? So there's really this competition for shader processors on the GPU. So by adding another shader stage, it means you're taking away from either a vertex shader or a pixel shader, for example. So if you can do everything on the VS, it's better to do it that way. Some of the advanced shader features are things that maybe aren't used so often, include the Vertex ID and the instance ID, and these are both system values that get passed in as parameters. Also, as I mentioned earlier, UAVs are something new that you can bind as output to the Vertex shader. And also, this isn't a new feature, but just being able to use a null vertex buffer. Because the vertex buffer, the vertex shader can create its own data. You don't need to pass in the data to the vertex shader, and I'll show why that helps. So first of all, the vertex ID. One of the things you can use the vertex ID is to decide which vertex is currently being worked on by the vertex shader. So here's an example where it's using that information to fetch from a bound shader resource view. And as you can see, the vertex ID gets passed in as a parameter, and that tells the system that it needs to generate a vertex ID, which can be used in the shader program. And in this case, it's just using it to look up a vertex value in a buffer. So a couple little details here. If you're doing a draw call, every ID is going to increment with every invocation of the vertex shader. And if you're using a draw indexed call, every invocation of the vertex shader is going to have the next index in the index buffer. So UAV buffers are nice to have. So these are uniform access view, unordered access views. And now you can write to them from a vertex shader. It's a really powerful feature. One of the things you can do with it, for example, is something like stream out. You can just write out your vertices that you've processed in the vertex shader. It has a couple nice features, though, that it's not limited just to strips like stream out. You can output whatever format you want, and typically the format you want to output are triangle lists. So you can do that directly. Also, it's powerful just because you can output any data you want. Anything can be output to the UAV. And as I mentioned, null vertex buffers are a way to tell the vertex shader that you just want to create the vertex data yourself. All you do is set the number of vertices in the draw command, and the vertex shader will execute fine without a vertex buffer. Now, one of the ways you can use that is to do a kind of instancing. There's a number of ways, things you can call this. I've referred to it as vertex shader instancing. You can call it shader instancing. I've heard it called smart instancing or soft instancing. But I'll be referring to it as vertex shader instancing in this talk. So basically what you do is you call draw with a total number of vertices, and then you can bind a mesh as an SRV and also your instance data as an SRV, and then just look them up directly from the vertex shader using the vertex ID. So now I'm going to go over some specific techniques. I'll start with something really simple, which is a full screen triangle, and then something more complex with vertex shader instancing. I'll also talk about merge instancing, which you may have heard of, and then finally talk about using UAVs in the vertex shader. So first of all, full screen triangle. You've probably all heard that if you're doing post-processing, the most efficient way to do that is not with a full screen quad, but with a full screen triangle. And the reasoning behind that is because you don't have that triangle edge going down the middle of the screen, and because of the way that the hardware outputs pixels in groups of 4, it would have to duplicate it along that diagonal, so it's less rendering. And this is very easy to do with all completely self-contained in a Vertex shader. You don't need to create an index buffer or a vertex buffer. You don't even need to create a constant buffer to pass to the Vertex shader. So what we're going to do is output these clip space coordinates, because that's what the Vertex shader passes to the next stage. And as you can see here, the bluish colored rectangle is going to be the screen, the full screen, and then the triangle is actually larger than the screen. And we're going to use texture map coordinates to place your full screen image onto that screen. So because it's the most efficient way of doing it, everybody should be using this, really. There's no reason not to. Here's the C++ code for doing this. It's really pretty straightforward. We're just binding a null vertex buffer and index buffer. We don't need a layout either. Set that to null. Bind the vertex shader, set the topology to triangle list, and then just draw 3 vertices. Really simple. And then here's the HLSL code for doing that. So it's a little bit maybe non-intuitive what it's doing at the first part there. We're passing in the vertex ID, and we're taking that vertex ID and kind of manipulating it so that we're getting the correct clip space coordinates. So the inputs are going to be 0, 1, and 2. And so the first vertex we get is going to be 0. And what I do when I try to figure this out, it's kind of just a fun little game to play almost. It's kind of fun to work this out. But actually, you just take the input and see how that would map to the output. And eventually, you can come up with a simple formula like this for doing that. Usually ends up with some integer divides and mods. You almost guaranteed that. And it's doing the same thing here for the texture coordinates to determine those. So the next example I want to give is point sprites. And this is a little bit more complicated than doing just a simple triangle. Usually, we see this being done in the geometry shader, but it turns out it can be faster to do it on the vertex shader. You, first of all, you can create a shader resource view, which is your point buffer. And this is, for example, a particle system. It might include all of your particles' positions. And then this gets bound to the vertex shader stage. You then call draw or draw indexed to draw all of the triangles for that particle system. Then in your vertex shader, you read the location of that point using the vertex ID. And then you expand that point to a quad. So I'll go into more detail about that later. One use for this would be for doing particle system. Another one would be doing something like bokeh depth of field. If you've seen that, it takes the circle of confusion, the blurred area, and for each low-res pixel in there, expands it to a sprite, which gets rendered as a bokeh shape. So since you have a lot of pixels there to do that, it's a lot like just drawing a particle system, and you can use this same technique. Now, one thing we do recommend is don't do this for don't use draw instanced for a small mesh. It's better to use draw or draw indexed. And here's the C++ code for setting it up. Basically, we're binding that particle buffer, which has the positions, setting the topology to triangle list again, and then also you see the particle count times 6. Times 6 because we have 6 vertices because it's a triangle list, a quad. Pretty simple. Now, this is the HLSL code. It's only slightly more complex than the single triangle. First thing I want to point out is something that's pretty common with this type of thing is we take the instance, the vertex ID, and do an integer division by the number of vertices. Now, since this is draw indexed, we're going to get repeated indices. So there's only 4 unique vertices per index, per quad. So we divide by 4, and that gives us an offset into the particle that we want to draw. So that tells us how to look up the particle position. And in order to determine which vertex within the quad we're working on currently, we do a mod with 4. So pretty common. And then we just use that information to look up that data into these buffers, this buffer that was bound with the position and the color. So this is the performance results I found. I put together a synthetic test that just ran a bunch of particles, 1 million particles and 500,000 particles. And the one on the left is 500,000 particles, and you can see how performance on the far left is the indexed, if you can't see there, is the indexed draw, and that's the fastest. And then the next fastest is the straight draw with no index, and then the geometry shader, and then next to that is draw instanced. And you'll see that in both AMD and NVIDIA that the performance is a lot worse with using draw instance. So like I said, this isn't something we recommend. So draw index, just to summarize here, draw index is the fastest method. Draw is a little bit slower. Has some advantage because it doesn't need an index buffer, so you're saving some data there. And then once again, don't use draw instance for creating these kinds of sprites on either AMD or NVIDIA hardware. There might be better ways to do it. In this particular technique, it's just not a good way of doing it. Okay, so now the next type of instancing I want to talk about is something called merge instancing. And you might have seen this before. It's been presented at other conferences, and I think there are some games that still are using it now. And the way it works is it combines multiple meshes so that they can all be instanced at once. The reason why you might want to do this is, well, first of all, batching. If you want to have more triangles in a batch, and batch as much as you can, and this helps you do that, so you have fewer draw calls. Another reason for doing this is because you can have localized bounding boxes. With instancing, you don't know where you're placing your instances. They could be all over the map, and then your bounding box is huge. But if you instance based on location, you can have tighter bounding boxes, which means they're more useful. Now, the way it works is each mesh is in a fixed page in the vertex buffer, or in the vertex data. And that means there's a fixed count for each mesh. Now, for meshes that are bigger than a page, you can break them apart across multiple pages. And if they're smaller than a page, you can add degenerate triangles at the end. So here's a kind of a pictorial representation of this. On the left is the instance data, and you can see how it contains offsets to meshes. And on the right is the mesh data, which actually contains the vertices. So as I mentioned, these are all fixed length. They're all the same length. And if you have some extra space at the end, you can just add a degenerate triangle. So the best way we found to do this is to actually just do it in the vertex shader. You can use the vertex ID, which I mentioned before, in a similar way where you do an integer divide by the size of the mesh. Because remember, this is a fixed size mesh, so it's always the same. And that gives you an offset into the mesh that you want to render. And it turns out it's faster than using draw instanced for this. A specific example we found was with the game Star Citizen, which is being developed by Cloud Imperium. And they've got this test which is using merge instancing. Their goal here is to reduce the draw call count. And they're rendering 13.5 million triangles, about 40 million vertices. So a lot of stuff being drawn on the screen. And they did one with draw instanced, and it was using the instance data in a Vertex buffer, and then also had this soft instancing, which is the Vertex shader instancing, which uses the Vertex ID to grab the data from a SRV. And as you can see, the soft instancing on the right is much faster, both for AMD and NVIDIA. And you can see if the draw instancing, in this case, AMD was actually a lot worse than NVIDIA, but improved to almost exactly the same. And both vendors got an improvement with that, with the software instancing, or Vertex shader instancing. So the last thing I want to talk about is Vertex shader UAVs. And this is random access reads and in particular writes to a Vertex shader, from a Vertex shader. They can be used to store transformed Vertex data for doing multipass algorithms, just like stream out can be used for that. But as I mentioned earlier, they can be used for storing any kind of data at all. One other thing they might be used for is for passing constant attributes between shader stages. Instead of having additional attributes passed as parameters to Vertex shader stages, you could put them in a UAV, which later gets read by that pass. So an example of using a UAV is skinning. So you could skin the Vertex data once, skin the mesh once, save it into a UAV, and then use that UAV multiple times for either instancing or drawing your shadows or for doing reflections where you have a multipass algorithm, anything like that. But it could also be used for something that may not be instance. Well, okay, shadow map rendering I mentioned here. The thing is, though, the real power of these UAVs is that they allow you to write out anything, not just stream out vertices. You can write out whatever you want. And that was a kind of a big limitation on Vertex shaders. So one of the things you might want to do is output a bounding box. You can calculate the bounding box extents in the Vertex shader and then just use a UAV, a very small UAV, which stores the bounding box. One thing you have to do, because everything's running in parallel here, you need to use atomics. I used interlock min and max to determine the min and max of the bounding box. And then, oh yeah, one note there is you use integers for that. You then could store this bounding box for use in a later pass, maybe for doing things like GPU physics, collision data, or maybe tile-based processing. There's a lot of tile-based processing where you're comparing bounding boxes. So it could be useful for that. And here's the HLSL code for doing that. Pretty simple. It's kind of a snippet, not the whole thing. And it's showing, well, you start out by skinning the Vertex data and then storing, and then keeping that value, and then doing a min and max on the UAV. And you noticed here I'm doing a little bit of a hack here where I'm scaling the data to do a conversion to integer. And it works pretty well. But there might be more clever ways of doing this. All right, so another thing you could do with a UAV, just while we're talking about ideas for that, is to do a single pass GPU-only particle system. So how can you do that? Well, in the Vertex shader, you generate the sprites for rendering. As I mentioned earlier, you can use the instance ID, the Vertex ID, to look up into the bound SRV to find the vertex, the position of the particle. Then you use a UAV to store your particle state. So you do your Euler integration in the vertex shader and then save out the state so that for the next iteration, you can have that updated state. And it's all done in the vertex shader. So it's not only a GPU-only GPU-only particle system, it's almost a vertex shader-only particle system. Here's the HLSL code for doing that. Should look pretty familiar. We determine what is the index for the particle, which quad we're working on, or which vertex in the quad we're working on. We then look up the position. And then we also want to look up the state. So the state is storing the position and also the velocity. And then we use a delta t that gets passed in as a constant buffer, part of the constant buffer, and use that for doing the integration to find the new velocity and the new position, and then save that out as a state. In this example, I was using an SRV to store this, to read in the state, the particle state, but you should be able to just use the UAV for both reading and writing. So just a single UAV. And yeah, that's about it. So just to go over some of the takeaways of this. These vertex shader tricks can be more efficient than some of the commonly used, maybe naive methods of using the vertex shader. You can be sure to use this vertex ID for doing smarter type of instancing, vertex shader instancing, I've been calling it. It can be used for things like doing sprites or this merge instancing where you have multiple meshes. And also UAVs add a lot of freedom to vertex shaders for doing things maybe like bounding box calculations or, as I just mentioned, a single pass particle system. And if you have time, I can just run something. Here's some acknowledgement and thanks. And also, I can take questions now if you want. Is that right?
Hello. Right here, to your right.
Oh, yes, go ahead.
I wonder if it's any better to use Vertex for skinning, for example, rather than compute.
Sorry, I didn't hear that.
To do the skinning in a Vertex shader like this with the instancing rather than with the compute. Would that be better because there's no separate compute queues involved or what?
Yeah,
I mean,
Vertex.
why would you do this instead of compute, for example?
Well, why would you do this instead of compute? Well, one reason might be you can do the draw. You have a single draw call instead of a separate draw and dispatch.
No, I mean for still using the UAV, like you just skin once. Like typically you would just, like now since the UAVs are there, you can just use them as stream out. You do the skinning once,
right?
But traditionally you could do that with compute, right? And so I was just wondering if there's any advantage or disadvantage.
Well,
to one
like
or
I'm saying, the one advantage I can think of, and I don't think there are many advantages, because using compute is probably a good idea, but one advantage might be is you could do the draw, the first draw,
right,
and then the second draw you use the stream out data.
Okay. All right. Thank you.
Yeah. Do we have time? Or we have time for demo.
Can I ask one more question?
Yes, go
Quick
ahead.
question, sorry.
Yeah.
I want to confirm something about the merge instancing example.
Yes.
You are using unindexed geometry, judging from the number of triangles and vertices. Is this correct?
We're using, no. In that merged instancing example, it's just a draw, not indexed, I believe.
Yes. So you are not using indices.
Yeah.
So it goes direct. I'm not exactly sure how indices can work with this. So it goes directly against the performance advice from the beginning of the talk. I guess I'm just curious as to why this can be useful. You are amplifying your geometry like at least 3x, in reality like 5x. Vertex count, I mean, not triangle count. What do you actually save? Like, is the batching that important? Like, is the batching that better?
Well, the performance improvement was from not using draw instanced, from going from draw instance to draw.
Yes, but if you used indexed geometry for instancing case, it might have been faster.
I think you're right. We haven't tried that.
Okay, thanks.
Okay.